Hello everyone, my name is Subhash Sharma. Joining me today are my colleagues Rishi Soni and Rishabh Chaudhary. We are final year engineering students from Purnima Institute of Engineering and Technology, Jaipur. Today we are excited to present our final year project exploring intelligent traffic signal optimization using computer vision and real-time vehicle density analysis. Traffic congestion is a major problem in urban areas. Most existing systems are static timers, which do not adapt to real-time traffic conditions. As a result, even when a lane has very few vehicles, it still gets a time signal time, leading to unnecessary delays. Our project aims to solve this problem by using computer vision and AI to dynamically adjust traffic signals based on real-time vehicle density. Our system works in two main parts. First, we detect and count vehicle using computer vision. Then, we use the data in an AI-based traffic controller to optimize signal time. Now, I will explain the vehicle detection part. For this, we use YOLO, which stands for You Only Look Once. It is a real-time object detection algorithm. Here is a vehicle count.py. We load the YOLO model using OpenCV's deep neural network module. This module is pre-trained on the COCO dataset. Since YOLO detects my object types, we filter only relevant vehicles, classes such as car, bikes, buses, and trucks. Each video frame is converted into a blob and passed into the neural network. The network processes the frame and output detected objects along with their bounding boxes. As we can see on the screen, the system is detecting vehicles in a real time. Each vehicle is enclosed in a bounding box with its class label. At the top, we can also see the count of vehicles moving in different directions. This detection module forms the input for a traffic management system. Now, my teammate will explain how we track and count this vehicle accurately.
Thank you. Detection alone is not sufficient because the same vehicle may appear in multiple frames. If we simply count the same vehicles multiple times. So to solve this, we are using a tracking algorithm called Euclidean distance tracker. So here I will show you this. Here we calculate the Euclidean distance between the center of the current detected object and previously stored object positions. If the distance is small, we assume it is the same vehicle and update its position. If no matching object is found, we assign a new unique ID to the vehicle. This ensures that each vehicle is tracked individually across frames. Now, once tracking is done, we can count vehicles based on line crossing as given in this function. We define virtual lines on the screen. When a vehicle crosses these lines, we increment the count. This method ensures accurate counting without duplication. We also maintain separate counts for different types of vehicles, which helps in better traffic analysis. Now that we have accurate vehicle counts, the next step is to use the data to intelligently control the traffic signals. My teammate will explain this based on the AI-based traffic control system.
Thank you, Rishi. Start the simulation. Now I will demonstrate the working of our AI-based traffic management system using this simulation. This simulation represents a real-world four-way traffic intersection where vehicles are being generated dynamically. As we can see on the screen, vehicles are continuously being generated in different lanes. Each vehicle has its own type, such as car, bike, bus, truck, and even ambulance. And each behaves differently in terms of speed and space. This randomness helps us simulate real-world traffic conditions which are never perfect and perfectly predictable. So now focusing on the traffic signals, unlike traditional systems, these signals are not following a fixed timer. Instead, the green signal duration is being calculated dynamically based on number and type of vehicles present in each lane. For example, if we observe this lane, it has a higher number of vehicles. So the system automatically assigns a longer green signal time to this lane. This ensures that congestion is reduced and more vehicles can pass efficiently. On the other hand, lanes with fewer vehicles receive shorter green signals, which avoids unnecessary waiting time. So essentially, our system is making real-time decisions based on traffic density instead of blindly following a predefined cycle. This is where the AI-based logic improves efficiency significantly. Another key feature of our system is emergency handling. If an ambulance appears in any lane, the system immediately prioritizes that lane and gives it the green signal. This ensures that emergency vehicles are not delayed, which is a critical real-world requirement. Now, one problem with dynamic system is that some lanes might get ignored if they always have low traffic. To solve this, we have implemented a fairness mechanism. Even if a lane has few vehicles, the system ensures that it gets a green signal after a certain number of cycles. So, no lane is starved or ignored. We can also observe that signal switching is not sequential like 1, 2, 3, 4. Instead, the system intelligently decides which lane should get the next green signal based on priority, density, and fairness. Because of this, our system reduces unnecessary waiting time, improves traffic flow, and minimizes congestion. We can also track how many vehicles have passed through each lane, which helps in analyzing traffic efficiency. So overall, this simulation demonstrates how our AI-based system adapts in real time to changing traffic conditions, making it far more efficient than traditional traffic signal systems. Thank you.